So I'm taking another look here at Robert E. Whaley's paper in the Journal of Finance. It's an early paper, it's a 1986 paper, and it relates to the valuation of American futures options. And figure 1 here in the paper reveals a number of insights in relation to the relative value of American and European options. So if we just expand a little bit here, the graph, a few interesting things kind of emerge. First of all, just to what we have here is in figure 1 we have European and American call option prices as a function of the underlying futures contract price. So both options are based on a futures price, and we have the exercise, which is X, and on the vertical axis, then we have the value of the European. The lowercase c here denotes the European option, and the capital C, the American option. And if we had some color here, it might help, but first of all, there's two, if you like, boundaries that are revealed here. There's a boundary for the American option, which is very clearly f minus x, okay, or maximum of f minus x 0, because it does go to, there's no negative region here on this option, so it is actually maximum f, the futures price, minus the exercise price, or 0. And then we have the lower bound on the European option, which is f minus x e negative rt. And again, there's no negative range here on the European option either. So the lower bound here for the European option is this straight line stretching at close to a 45-degree angle, but shouldn't be quite 45 degrees. And then this other boundary, which also is going 1 for 1. So as we increase f, we increase in a linear fashion the payoff on that option. So it's, if you like, what it represents here, if you exercise early, how much can be attributed to the value of the option in kind of real time if the option is exercised early. Okay, now when we look at the American option, the boundary for the American option, so we have a time value for the American option, we have the time value for the European option. The time value for the American option at some point just becomes tangent with the lower bound here, the f minus x, and doesn't go below. Okay, it has to either be in excess or equal to f minus x, whereas the European option, in contrast, its value can be either in excess of f minus x e negative rt or something higher. So it can actually drift lower, and it does so, and it cuts, would appear here, it cuts at a slightly higher level, certainly a higher level for f, okay, and may go below, cannot go below, okay. So the lower bound here is actually, regardless of the time period, right, the lower bound here, the value of the European option cannot go below this f minus x e negative rt. Okay, so I'm going to go into Excel for a moment and take a look at a worksheet that I had developed using Leisen Reimer, and in that instance, the option was developed, but for a spot price. Okay, so with a Leisen Reimer formula, Leisen Reimer truncate, and we can have a look at the code here. I'll leave the code below in a link, but the Leisen Reimer code here is based somewhat on Espenhogue, but I've added some addition to the code so that the zero region can be truncated, and by truncating the zero region in the code, the overall effect is to speed up the code, but the code is actually relatively fast because we're dealing with dynamic type of construction in terms of the code. But when we look here in terms of the option, we don't quite have a futures option because this model is based on the spot price, and our boundaries here, S minus X and SE negative QT and KE negative RT, the boundaries for the American and for the European option are done when we assume that there's a dividend yield and that the underlying is the spot price. However, if we were to change this, let's say we took another look at the so I move into this other worksheet, and I do a couple of things as I transition into the other worksheet. So I no longer I'm looking at the spot price. I'm going to say it's the futures price, and the generally speaking, the option on the spot can be revamped so that it becomes an option on a futures if we make a few changes. So if we change S to F, and we change the we ensure that the R is equal to Q, so the risk-free rate is equal to Q. So in both instances, we're saying if the risk-free rate is equal to 5%, we set arbitrarily the value of the dividend yield equal to 5 also. And if we run the valuation here for both the Leisen Reimer, if we run and Black Scholes, the value that emerges would be equivalent to using a futures contract. How do I show that? Well, one way of showing that is I could introduce the Black model here in the estimation, Black 1976, and I have some code in the Black model. So we've if I just open up this snippet of code here, okay, we could have a Black call function where we have both we have a call and we have F, K, R, sigma, T, which are the standard variables in a Black model. So if I insert into this particular workbook, okay, so if I come out of here and go into this particular workbook modules, okay, it's not allowing me, so I'll try that again, and I'll say insert, okay, module, so it's a new module, it'll be module 1, and I just paste in the code for a Black call, and I'll rename that as well. I'll just call it Black 76, Black 76, okay, and hit return. Now if I go back into we'll just take these values here for a moment, Black call, copy, Black call, and then the variables, parameter inputs, okay, and I come down here and I'll just paste, so I could paste below, edit, paste, and then I'll paste again here, paste, so edit and paste, and then we'll say we'll put an equal sign, so Black equal to Black, and then for F take 100, for K we'll take again the exercise price, for the risk-free rate we'll take 5%, for sigma take 30%, and for T we'll take 5 years. So T is equal to 5 years. When we return that value, we get 204578, 2045. Okay, so while the Leisen Reimer model is slightly out, only has 10 steps, the Black Scholes model 104578756 is yielding the same result as here for the Black 76 model. Okay, now what does that reveal? That reveals that the Black Scholes model can be used if we have an option on a spot, we can revamped that so it becomes an option on a futures, moving from the Black-Scholes to Black formula. All that's necessitated is that the risk-free rate is set equal to the dividend yield, and the spot then becomes the future. Okay, so we have a value here then for the Black model, 204578, and that's consistent here. And with a 10-step Leisen Reimer model for European option, which is a call, we get a close approximation of 2045. Okay, so second thing then is we have a second Leisen Reimer function, and it's making the same estimation except the option is American. And when we examine, if I then create a data table where, for instance, here I have a set of values for the option ranging for different future prices. So these are each individually future prices increasing at steps of 10. And if I were to rerun, so for instance, let's remove for a moment these two sets of data. When I remove those, delete, our models collapse to intrinsic American, or the lower bound on the American option, lower bound on the European option. Okay, now if I was to re-estimate the European option and American option, okay, for those different future prices, to set up the data table, I set just underneath E here, I set this cell equal to where we estimated the Leisen Reimer European option and the American option the same. Then to rerun the futures estimation, both the European and American estimation using Leisen Reimer on the futures contract, we go to data, what if analysis, data table, and then do we have a column or a row? We have a column of data, and what in the original parameter input was the futures price. Then we hit OK, and it fills in quite fast. Why? Because we only have 10 steps here in our Leisen Reimer formula, and it's yielding relatively high degree of accuracy with 10 steps. Okay, that's one of the advantages of Leisen Reimer. Okay, now when we investigate this, what we observe is we can, in this instance, move away from using the futures and forwards. So we should redesignate the diagram here, and I'll do that. So we have an intrinsic value. Let's just take this graph over to one side. And if you like, where are we getting this value from? Well, it's this intrinsic. Do that again. It's the blue actually I want to highlight. Try again. Yeah. So where am I getting this intrinsic? It's just very simply, it's the lower bound for the American option. Rather than S, we have F. And we could add one more detail for the lower bound in the American option is maximum of F minus X, comma, 0, close brackets. Okay. Then the second thing, the lower bound for the European option is no longer this. In fact, it's using the notation in Whaley. The lower bound on the European futures is F minus X E negative RT. So that's actually represented here by the orange. Okay, so it's the lower bound European, and then we should change this to maximum of S minus X. So I'll right click, select data, and we'll just change from S to F. Okay, and we run it, and we can just bring that down again, and maximum, the blue here, is denoted by F minus X. F minus X or 0, and the lower bound for the European option is the orange configuration here, and that's given by maximum of f minus